All right.
George, start.
All right, we can perhaps start, or should we wait longer?
I think we can start.
I think we can start.
We can start, okay. So thanks everybody for coming to the virtual seminar today. We are very happy to have Zahra Khanian here to give a talk. Zahra graduated from University of Barcelona in 2020, and with Andreas Winter and Maciej Levenstein from the physics with PhD in physics department. And then since then she is in Technical University of Munich working with Robert Koenig. And today she will speak to us about rate distortion theory for mixed states.
Thank you so much, George, for the introduction. Yes, probably there are audience from different departments, so feel free to ask questions if you have any questions during my talk. As George mentioned, I'm going to talk about rate distortion theory for mixed states, which is a collaboration with Kohtay Kroeva and Debbie Leung in University of Waterloo. So rate distortion is a data compression problem. So it's nice. First, I introduce a bit of data compression in the quantum physics. So quantum data compression was pioneered by Schumacher. Schumacher defined a very simple model of a quantum data or a quantum source, which is a quantum generalization of Shannon's statistical source. Schumacher defined a quantum source as an ensemble of pure states. Each of these states, psi xa on system A, are generated with probability px, and we assume that there is a source which generates n IID copies of this source. So it means that the source generates this psi x on system AN, which is a tensor product of each of these psi x's in some subsystem A1 till AN, and each of these states are generated with probability px. And okay, so what do we mean by compression? We mean that, so assume that we have this sequence of quantum states and we want to compress it. That is, we want to apply a general quantum operation, which is generally a completely positive trace preserving map, and we map it to a system Mn. And we want the dimension of system Mn to be much smaller than the dimension of system An, which is original system. But after compression of the information, we want to be able to recover it somehow. So there's going to be some decoder that takes the compressed information AM and maps it to the output sequence of data. And we want the output sequence of data to be as close as possible to the original data here. And we define the error or the figure of merit as 1 minus the average fidelity between the input and output sequence. Fidelity is actually a very useful functional because it's a measure of how similar two quantum states are to one another. So if psi x and chi x are exactly the same, then the fidelity is equal to 1. If they are very different or orthogonal, then fidelity amounts to 0. And essentially, Schumacher proved that the minimum compression rates, which is equal to the log of dimension of this system Mn over n, which is the number of the terms in the sequence, is equal to the von Neumann entropy of the ensemble. That's Schumacher's main theorem. So, okay, so I explained that the error that Schumacher defined for the compression tasks is equal to 1 minus the average fidelity between the whole sequence of input data and output data. There is a very interesting phenomenon happening in this compression problem, and it's as follows. This is called a strong converse property. So suppose that we want to compress the source just a little bit more than the optimal compression rate, which is the von Neumann entropy. So it's proven by Josa and Schumacher in 1994 and for special cases, and also later by Winter for the general decodings, that even if we want to go epsilon amount below the compression rate, all of a sudden the error jumps to 1. It means that we can never have a trade-off between error and rate. Whenever we want to compress the information just even a little bit below the von Neumann entropy, all of a sudden error jumps to 1. This is called a strong converse property. Okay, so rate distortion is a specific modeling of data compression which allows us to have a trade-off and the error suddenly doesn't jump. So suppose that we have a similar setup to Schumacher. That is, we have the input data, we want to compress the information, and then we want to recover. And this is the output, chi-an is the output sequence of data. In this case, let's imagine that we are considering a looser error criteria. That is, instead of taking the fidelity between the whole input and output sequence of information, we only considered fidelity between the first system of the input and output, the second system, and so on. So I just remind you that in the Schumacher case, the fidelity is defined for the whole input and output data. But here, what we rather do is just compare all the systems one by one. This is called the local error versus the block error that Schumacher considered, and local error is a looser error criteria, because if we have a fidelity for the whole block of states, then this implies the fidelity for each of these subsystems because of the monotonicity of fidelity under partial trace. And we know that from classical information theory, actually, and also in quantum information, when we consider this looser error criteria, instead of having a strong converse property, we can have a trade-off between rate and error. That is, if we want to compress more, we can do it, but in the expense of having larger error, but not error equal to 1. Okay, that was what was done for pure quantum states, or the sources that consider like ensemble of pure states. But so let's talk about a bit the history of sources that are mixed states. So imagine that we have an ensemble of these mixed quantum states compared to Schumacher that consider pure states. Here we can have any general quantum state here. So this problem was studied for the first time by Kouachi and Emoto in 2001. So Kouachi and Emoto considered this problem, this source of mixed states, and the compression is similar to the Schumacher case. So there is a decoder that maps the information, and we have like the block fidelity similar to the Schumacher case, and Kouachi and Emoto proved that the optimal compression rate is equal to some subsystems of system A. That is, the information that the amount of information that we can compress in this case can be smaller compared to Schumacher. Then for this problem, there is another variation. So suppose that the encoder can see the index of X, the index of the states that are coming from this ensemble. This is called the visible compression, because the encoder can see the identity of the signals. This is similar to the previous case. We have a compression scheme, and then we recover. Again, we have a block fidelity, and this problem was studied first by Horodecki, and later Hayashi showed that the rate that Horodecki obtained was equal to regularized entanglement of purification. So these are two variations of mixed state compression. The difference with the Schumacher case, that is when we have ensemble of pure states, is that it doesn't matter whether the encoder sees the xn, this identity, or not. In both scenarios, the optimal compression rate is equal to von Neumann entropy of the source. But when we have mixed states, depending on the case that our source is blind, that is doesn't see index X, or if it is the index X, which is called the visible model, we can have different compression rates. So the strong converse property, considering this block fidelity, is one of the things that I have done. This is a paper that I studied the strong converse property for compression of mixed states. Okay, so rate distortion problem for mixed states essentially is a similar problem to compression of mixed states, but here we assume that instead of having block fidelity, we have per copy fidelity. We only compare one sequence at a time. We don't compare all blocks of data together. So let's define our problem in this case. So suppose that we have an ensemble of mixed states. There is another way to write this source. So we write the ensemble of mixed state as the form of these specific classical quantum states. There is this extra register X here that stores the identity of signal X. And essentially, this is just a classical system that it's an orthonormal basis for system X. And we can show that the average fidelity, which is the figure of merit for our compression scheme, can be written as the fidelity for the whole input states with system X and the output system with the system X defined here. Essentially, it's like system X is like a reference system that we want to preserve the correlation with throughout the encoding and decoding operation. So in the model that we consider, this is an interpolation of visible and blind scheme in the sense that we consider that the encoder has access to this extra system Cn. This is the C system. When system C is equal to system X, that is Cx's are equal to X, then it's like a visible compression. But when system C is a trivial system, it's like a blind compression. It's like the encoder doesn't see anything. So we consider this general model, then depending on the structure of system C, our model can be either blind or visible. So we have a similar compression scheme, the encoder information, and we want to reconstruct the information considering local fidelity. Then there is some extra register. Assume that the encoder and decoder share extra entanglement in registers A0 and B0. When we don't account for this amount of entanglement that they share, we say this is an entanglement-assisted scenario. But when they don't share any entanglement, we call this scenario an unassisted case. And also as for the figure of merit, in general, I said that for the data compression schemes, usually average fidelity, 1 minus average fidelity is defined as error. But here we consider a more general setting. We assume that we have a function, which is the only constraint that we put on that is that this function is continuous and convex. Actually, fidelity is just an example of such class of functions. But this delta is a like more general thing. And we assume that we want to reconstruct the data such that the distortion for each copy, the average distortion is smaller than D. And for a given amount of distortion or error, we call the minimal achievable rate as the rate distortion function. So this is our setup.
Zahra, sorry to interrupt you.
Sure.
Rabins has a, sorry to interrupt you. Rabins has a question.
Sure.
Hi, Zahra. Nice to see you again.
Hi.
So just had a question on the blind and visible compression scheme. So in the blind compression scheme, does it mean that the Alice just has access to the total density matrix, but does not have access to the individual constituent mixed states emitted by the source?
So in the blind case, it's like when you know that in the quantum case, if we have a set of states, we cannot distinguish them perfectly, right? Because if we do a measurement, it might destroy the states. So, right. But when we see X's, it's like we know the encoder knows exactly which states it's compressing. That's the visible case. But in the blind case, if the encoder wants to identify each of these states that are being input to the system, then it has to measure, and by measuring it destroys the information. So the access is only different in having access to system to this number xn. That's the only thing. Otherwise, they both have access to system an.
Okay, so in the blind, okay, so in the visible case, Alice knows exactly what states are emitted at each time steps, right?
Yes, yes.
Okay, thanks.
Sure. So this is one of our main theorems that we found the rate distortion function, that is the optimal compression rate for a given distortion in the entanglement-assisted case. In the entanglement-assisted case, as I mentioned, we assume that the encoder and the decoder share these extra registers A0 and B0 in maximally entangled form, and we don't account for how many maximally entangled states they want to use. So essentially, we consider it to be free. And we find that the rate distortion function is equal to this minimization for over CPTP maps for this mutual information. So here one important point is that the rate distortion function is a single letter function, meaning that it doesn't depend on the whole sequence of states. It only depends on one copy of the state. So since it doesn't depend on all of the copies of the states, it's easy to compute this mutual information. So it's like this mutual information is with respect to this state tau here, and how we can define tau is as follows. So suppose that we have this state rho ACX, which is our source. I defined it here. So we consider a purification of this state, and then by register X prime is that one extra register that purifies this source, and then we apply this CPTP map N, and there is a constraint on this CPTP map that should have a distortion below D, and then we obtain the state tau, and this mutual information is with respect to this state tau. So we essentially prove that when we have free entanglement between encoder and the decoder, the optimal compression rate is equal to this optimization problem. But it's not very difficult, as I said, to compute this optimization problem because it's just a single letter formula. It doesn't depend on n, the number of systems, because in all of these problems are asymptotic problems. So n is an variable that goes to infinity. So if this depends on n, then that would be much more complicated to compute the optimal rate. So then there is another scenario that we call it unassisted case. In unassisted case, we don't let Alice and Bob, the encoder and decoder, share entanglement. So in order to talk about and introduce the optimal rate for the unassisted case, I need to introduce a quantity, which is essentially an entanglement measure. So suppose that this is called the entanglement of purification, which was introduced by Terhal and co-authors in 2002. So suppose that we have a state, bipartite state, rho AB, and the entanglement of purification for this state is defined as follows. So consider a purification of this state rho AB. Register R is a register that purifies the state on the whole system. And then look at the von Neumann entropy on only system A and R. So trace out system B and look at the entropy of system A and R. And consider that there is an CPTP map from system R to E. And we want to minimize this von Neumann entropy over all such CPTP maps. So this is essentially a optimization problem, and we want to minimize the von Neumann entropy over all such CPTP maps that map system R to another system E. So one thing about the entanglement of purification is that we don't know if it is additive, meaning that if we have many copies or tensor product of states, then we don't know that entanglement of purification is going to be the sum of entanglement or purification for each of these subsystems. This has been an open problem for a while, actually. So, for example, for other entanglement measures, such as entanglement of formation, we know that it's not additive, but for this one, we don't know if it is additive or not, even though there are strong suggestions that it is not additive. So this is the second theorem that we prove in the paper. It says that when we don't have entanglement between encoder and decoder, the optimal compression rate for a given distortion is equal to this quantity here. This quantity is much more complicated compared to assisted case. It is in terms of entanglement or purification that I already introduced. Also it involves optimization over some channels that applied on many copies of the state, and this channel is supposed to preserve the distortion for the overall state below D. And this entanglement of purification is with respect to state tau. And the state tau can be defined by considering purification of the source, as I explained in the assisted case. So we compute this purification of the state. We apply this CPTP map NK function and obtain the output state and compute the entanglement of purification for this output state. The difference between assisted and unassisted case is that in an unassisted case, this optimization depends on all of the subsystems together. So it's essentially is an optimization over unbounded number of systems. So we don't know how to compute this distortion function, and in general, even if entanglement of purification was additive, that is, we could write this entanglement of purification as sum of the entanglement of purification for subsystems, still we have this CPTP map, which acts on all of the systems together. So in principle, in order to simplify this rate and compute it, we need so many different things. For example, additivity of entanglement of purification, and to be able to show that it is enough to do the minimization over tensor product channels, which is very unlikely actually. So that was two main theorems in the paper. There is another theorem regarding when we want to have the trade-off between the entanglement and the quantum compression rate, which I don't discuss it here, which is much more complicated. But I would like to give you some ideas how we prove this optimal compression rates. So the achievability proof is usually like we find lower bounds for the rate. That is, we construct specific encoder and decoder, or a code that achieves a certain rate. So to do this, we use some other compression schemes such as Schumacher or quantum state redistribution, which is a well-known quantum compression protocol. And we show that by doing some local computation and applying these Schumacher and quantum state redistribution, we can construct a good enough code in our case. The converse proof, on the other hand, says that our compression rate is lower bounded by something. And this kind of lower bound proofs in information theory usually are called converse proofs. So to do the converse proof, we use some properties of the entanglement of purification function and mutual information function, for example, data processing, monotonicity of these functions under partial trace, for example. And also to prove the entanglement-assisted rate, we do a singularization, meaning that we lower bound this mutual information, which depends on n, by sum of mutual informations of individual systems. This is called singularizations, and this needs to do some techniques, and we use some specific quantum information tools to be able to do such lower bounds. This was some general proof ideas how we show that a given rate is optimal compression rate in our scenario. Okay, So as I mentioned, when we have a block error, as opposed to local error that we consider in this work, considering block error in the blind case, the case was studied by Kouachi and Emoto, and the optimal compression rate was the von Neumann entropy of two subsystems of system A. And we prove in the paper that in the limit of d going to 0, the optimal compression rate is equal to the rate of Kouachi and Emoto. And also this is actually proven operationally, meaning that we devise a specific construction, and using this construction we show this. But on the other hand, we also only using the quantities, we directly prove that if we do a minimization on the entanglement of purification of this specific form, we can show that it is equal to von Neumann entropy of two subsystems of the source. These are some specific cases of our analyzing the rate that we show that the rates have a very simple and specific form. So if I want to review what we have done in this work is that we consider data compression and we consider local error as opposed to global error. We consider a model which is a unification of blind and visible model. We don't distinguish them because we introduce this extra system C. If the system C is a trivial system, we recover the blind case. If the system C is equal to register X, then we recover the visible model. And so the other difference with the previous studies is that we consider a general distortion function. We only assume that it is convex and continuous, as opposed to considering only, for example, fidelity or trace distance. So in the entanglement-assisted case, we prove that the rate distortion function has a nice formula, which is a mutual information, and it is single letter form. In the unassisted case, that is when we don't have any free entanglement, then our rate is very complicated. We have proven a rate which is very complicated actually to compute. So it's very important to be able to analyze this kind of rates, but we don't know how to do that. Also, as I explained in the paper, we do the full characterizations of the rate region, meaning that we don't assume that the entanglement is free. We prove that there is an optimal trade-off between the entanglement and quantum rate. So if I want to say what is probably the biggest open problem here, or in general in data compression, for example, is that we have a lot of rates in terms of entanglement of purification and some other quantities, but we don't know if they are additive or not. If they are going to be additive, then it's very easy to compute them. But if they are not additive, we don't have any idea how to compute them. So I would say this is one of the biggest challenges in quantum data compression and rate distortion theories. And thank you so much for listening.
I have a couple of quick questions, I think, if you don't mind. When you talked about the general local distortion measure, you mentioned that it's only you said convex, I think. Okay. There's no monotonicity requirement here.
So monotonicity in terms of what?
Well, I'm thinking maybe I'm not clear on how you're defining of what you're trying to measure distortion wise. You have a local distortion measure between two different states, right? Between the original rho and the Xi state. Yeah.
Yeah, that's actually a special case. I mean, the fidelity is just a comparison between the input and output state that we can formulate it as a distortion function. But here, the function is only on the output state.
Oh,
Yeah.
so it's like the input is fixed somehow.
Yeah. Yes.
Okay. All right. And my other unrelated question was just these minima that you're trying to compute. Is there any hope of casting them as say in positive semi-definite programming, something like that?
I think in some special cases, when the function that we obtain has nice properties, yes, probably it can be reduced to STPs. But in general, I'm not sure about like how entanglement purification is gonna be able, whether we are gonna be able to reduce entanglement purification to an STP or not. So I don't exactly know, but I think that would be the case for at least for mutual information. Yes.
Well, thank you.
Sure.
Are there other questions?
Just one question. I think I might have missed this, but are you considering an IID quantum source in this work that emits mixed states, or?
Sorry, what was the question?
So the quantum source that you're considering here, is that an IID source that emits
Yes,
mixed
it's an IID source. So it's like we have this source rho ACX, and we consider tensor powers of this state here, which is basically considering an IID source.
Okay.
I want to say sorry because my video doesn't work, so it was it got distorted, I guess. So you said that the quantities that you computed in some cases at least is not known if they are additive.
Yes.
If you knew that they are additive, then you will also obtain that the purification of entanglement is additive.
No, entanglement purification, there are some suggestions, there is some work that shows by numerical methods that probably it's not additive actually.
But you got something that that incorporates that. I understand as a kind of the way that you define the entanglement scenario that you have incorporates the previous scenarios because you have visible, non-visible, everything here now.
Yes.
But if you get if your answer is additive, you don't get additivity for the purification of entanglement.
I don't think I understand the question, but maybe I explain this. So here you see that it's mutual. We have the mutual information, which like this is the case. This is the optimal rate. Whether we consider visible or blind, it doesn't matter. But this one can be single letterized, whereas in the unassisted case, we have this entanglement of purification over these many systems together. So my point was that we don't know if we can break up this entanglement of purification to some of the entanglement of purification of the subsystems. And probably it's not even true. That's the issue here.
I see.
Yes, so if I bring the definition, so suppose that I have an entanglement of purification defined like this for a given state. But suppose that I have the state row tensor row, okay? And then the first row is on system A1, B1, and the second row is gonna be on system A2, B2. So additivity here means that if I have entanglement of purification of A1, A2, and versus B1, B2, can I write it as the entanglement of purification of system 1 plus system 2 or not? And that's called additivity. But as I said, most probably it's not additive, no.
Right.
Yeah, I'm not sure if it answers your question, but
I think you did. Thank you.
sure.
Just a couple.
Are there other questions? If there are no other questions, let's thank Zahra again for her nice talk. As I said, my video doesn't work. I can go downstairs and join Maria and the rest of the people.
Thank you.
Okay, I'm gonna go downstairs, I think.
Okay. We'll be here. Yeah, so how long have you been in Munich now?
Now it's 3 years in a
Oh.
couple
Oh,
of
I'm gonna stop the recording if I can remember how.
Oh, yeah. Okay.
Oh,
It says stop recording, right?
oh, in? No.
No?
Oh, no.
Yeah.
Stop
Oh, stop
video.
video, you know, you're right.
Stop recording.
Yes.
Stop recording. After stopping, you will